So this is sort of a MetaBall fitting application. The idea, if I take us sort of to an initial state here, so the idea is that you start with a digitized surface of somebody, for example, of somebody's head or face. These things are made out of points. There are tons of points on it. If you can as you can see, he's got a whole bunch of little tiny dots. That's way more data than you need to represent the object. Furthermore, it's kind of hard to interpret it or to compare different surfaces because you have to figure out which point lines up to which point and so forth. The idea of this software is to come up with a much sparser representation of this head, and the representation that we're using is an implicit representation, which means that the surface, instead of being represented by a bunch of points on the surface, it's represented volumetrically as the level set of a bunch of radial basis functions. What's novel about this is there's not a lot of work on how to choose the centers of your radial basis functions when you're approximating a surface. This is early work, so let me start by showing you our current representation of this face. It's not adequate. We start with one primitive, and I said it's radial, which means that we're essentially thresholding of the distance from one point, and that gives us a sphere, which we would like to approximate the head as good as possible. So let's figure out the proper way to size that sphere. So it's actually doing Levenberg-Marquardt numerical optimization in order to determine where to place that metaball in order to produce the least amount of error on the surface of the mesh. So what you see now is color-coded. Gray points are really close to that implicit surface, and the blue points are on the inside and the red points are on the outside. Our aim is to keep adding metaballs and positioning them so that there's no red or blue, or at least we minimize the amount of red and blue errors. So what I can do is, if I show the metaballs, I can add a new metaball, and what it does is it looks for the area where the error was the highest, and the area that it found was on this subject's left temple. And you can see now, if I hide the meta object, that we've reduced a lot of that blue error on his side and substituted with red error on his ear. And if we look at the meta primitive, what we can see is that we have just created a dent in the side that makes it a little bit more head shape. If we repeat the process, we'll get another metaball, probably on the other side. And as this, if we allow this to just keep proceeding, we'll end up with metaballs. I'm going to load the previous one. So even when we have only about 6 metaballs, we have something which is beginning to look like an alien head. And this is research in progress, trying to decide how to steer or how to center these metaballs in order to get the best face with a very small, minimizing not the error, which is this. Really what we'd like to do is we'd like to get to a satisfactory error everywhere with a minimum number, in this case perhaps 7, of metaballs. A good template set of metaballs, we can move them slightly to capture the variation between one subject and the next. And the idea is that in general, doing alignment, registration, deformation, shape comparison, and other operations on this this very sparse MetaBall representation will be more effective than trying to deal with dense point sets or perhaps other surface representations. Oh, there he is.